Welcome to Deeksha online classes. What are we learning today? We are learning electric field calculations using Gauss Law. To understand it, let's go back to what we learned in the last class. What did we learn in the last class? We learned that the electric field due to a point charge is given by what? It is given by E is equal to 1 over 4 pi epsilon naught q divided by r square. That's right? Yes. And we also learned the principle of superposition, and principle of superposition tells us how to calculate the electric field due to multiple point charges. Then what did we do? We learned something about electric flux. And just recall that the electric flux is given by E dot dA, where E is electric field vector, dA is area vector, and this can be written as E dA cos theta, where theta is the angle between electric field vector and area vector. And what is this flux? Is it a scalar or is it a vector? It is a scalar quantity. And this electric flux idea is also explained using something known as Gauss Law. That's right. Let's just recall. Gauss Law tells us that the net electric flux over a closed surface is given by net charge enclosed divided by epsilon naught. This is what we discussed in the last class. Now, if we consider the electric field calculations due to point charges, they are very simple. However, try to imagine a situation in which you have, say, a line of charge. For example, you have a conducting wire on which charges are sprayed. Or imagine a plate, maybe a conductor or say conducting plate on which charges are sprayed. For example, visualize this situation. Or maybe a conducting sphere. You have a spherical conductor and imagine that the charges are sprayed on this conductor. Now the question is how to find out the electric field at a point near it. For example, at a distance r, or maybe at a distance r like this, or maybe at a distance r here. Now the question is, can we make use of what we learned last time? In theory, yes, but the practical challenges are huge. Why are they huge? They are huge because this setup, each one of these setups contain large number of charges. Thus, calculations become extremely tedious. So, in the case of the continuous charge distributions, what we learned all this time are really of not use. So we need to have a special approach as far as the field calculations due to continuous charges are considered. So how to do that? To do that, we will consider Gauss Law. What are we going to consider? We are going to consider Gauss Law. So let me remind you what that Gauss Law is once again. According to Gauss Law, net flux over a closed surface is net charge enclosed divided by epsilon naught. Remember, the moment we box an equation is the time to get serious, right? So flux is equal to q net divided by epsilon naught. Alright, now in order to understand the applications of Gauss Law, we need to understand something regarding charge density. So what is that charge density? Let's try to understand. Charge density, as the name suggests, is amount of charge present on a conductor or any distribution divided by maybe length, maybe area, maybe volume. There are three types of charge densities for our calculation. Number one, linear charge density. Number two, surface charge density. Number three, volume charge density. What are these three things? Linear charge density is charge per unit length. For example, you have a line of charge like this. Charges are all present everywhere on this line. And assume that this is a conductor of length L and the total charge present on this conductor is Q. Then the linear charge density is given by lambda is equal to Q divided by L. What is it? Total charge divided by total length. Many a times we need the charge present on a small portion of the conductor. For example, if I am interested in this portion of the conductor which contains an amount of charge dq, the length of that portion being dl, then we can also define that linear charge density as charge present on that small portion divided by the length of that portion. So lambda is dq divided by dl. So linear charge density is equal to charge per unit length. As expectedly, numerator is in coulomb, denominator is in meter. So coulomb per meter is its SI unit. Repeat it one more time. Linear charge density is charge per unit length. dq divided by dl. Alright. What is the next one? It is surface charge density. Here we can visualize something like this. A plate carrying a charge can be visualized and the charges are all present on this plate. Now assume that the total area of this plate is A and the total charge on this plate is Q. Then the charge present on this plate divided by its area gives us surface charge density. Sigma is equal to Q divided by A. Again, in calculations, sometimes we are interested in charge contained over a small portion like this. Now this portion is of area dA and it contains a charge dQ. Then dQ divided by dA is our surface charge density, sigma. So sigma is equal to dQ divided by dA. And again, as expected, coulomb per meter square is its SI unit. I repeat it one more time. Surface charge density is charge per unit area. And it is sigma is equal to dQ divided by dA. Now the last one, volume charge density. What is that volume charge density? Let us see. Try to visualize maybe something like this. This is an arbitrary closed structure. It is not a circle. Let's just assume that it is a ball which is pressed something like this. And the total volume of this setup is V and the total charge present here is say Q. Charge is present everywhere and the charge is Q. Then Q divided by V is nothing but the volume charge density, which is generally represented by the symbol rho. So rho, volume charge density, is charge per unit volume. Again, many a times we are interested in the charge contained here in a small portion. So let us take a small portion whose volume is dV and that contains a charge dq. Then dq divided by dV is our volume charge density, which is represented by sigma. You can notice that its SI unit is coulomb per meter cube. Alright, so let us understand these three one more time. Linear charge density is charge per unit length, and then what do we have? We have surface charge density, and this is charge per unit area, and finally volume charge density, which is charge per unit volume. So remember these three things: sigma, lambda, sigma and rho are the three essential quantities for our subsequent discussion. So this prerequisite is now clear to you, right? You may pause the video for a moment and internalize these three things before you take up the further discussion. I will continue here. You may pause and just have a quick understanding of these three things, by the way. So what was our objective? Our objective was to find out the electric field using Gauss law. Now how to find out the electric field using Gauss's law? To find out the electric field using Gauss law, here I am giving you the flow chart, or say the steps. Remember, the steps are very, very important here. What are all the steps? Let's try to understand. The first step is identify the symmetry. So now we are introducing something known as symmetry here. What are the three types, or what are all the different types of symmetries? Different types of symmetries are like this. One is what is generally known as linear symmetry or cylindrical symmetry. What is the meaning of linear or cylindrical symmetry? Linear or cylindrical symmetry refers to the case in which the charges are present on a line, or maybe on a cylinder, maybe a long line, maybe a long cylinder, etc. The second is what is called as planar symmetry. Isn't the word self-explanatory? Yes. Planar symmetry means you take a large sheet of charge and spray the charges on it. You have planar symmetry. The charges are present on a plane. The third is spherical symmetry. What is spherical symmetry? Again, the charges are distributed in the form of a sphere. So these three are the important types of symmetries. The first step here is to identify the symmetry. Whether it is cylindrical or planar or spherical is to be identified. Once we do that, the second step is to construct an appropriate Gaussian surface around the charge. Remember, an appropriate Gaussian surface has to be drawn. If it is a cylindrical symmetry, construct a coaxial cylinder. Let me repeat. For a cylindrical symmetry, that is for a line of charge, construct a coaxial cylinder. If it is a sheet of charge, try to construct maybe a cube or cuboid Gaussian surface. Sometimes this is also called as a pillbox. Clear? It is called as pillbox. Something similar to a cube or cuboid. Third is spherical symmetry. If the charges are distributed in the form of a sphere, your Gaussian surface should be a concentric sphere. So the second step is to construct an appropriate Gaussian surface. What is the third step? Third step is to use Gauss law. What is Gauss law? flux is equal to net charge divided by epsilon naught, or Q enclosed divided by epsilon naught. So now the key step is to find out what is the charge inside this Gaussian surface. So you need to calculate that. How much charge is enclosed inside the Gaussian surface needs to be calculated. Step number 4 is to find out the flux using this expression. d phi is equal to E dot dA, that is E into dA into cos theta. Many a times this is also written in this form. Flux is equal to E dot A, which is E A cos theta. You have already come across with this equation. Then the next step is to combine these two equations. That is E dA cos theta is equal to Q enclosed divided by epsilon naught. And the last step is to solve this equation for the unknown. What is our unknown? Our unknown is nothing but the electric field. So you may wish to pause the video here for a few seconds and write down these steps. The first step is identify the symmetry. Second step, construct an appropriate Gaussian surface. Third step, use flux is equal to net charge divided by epsilon naught. Fourth step, write your first principal equation for flux. Flux phi is equal to E dot A, that is EA cos theta. Fifth step, combine these two equations and write EDA cos theta is equal to Q net divided by epsilon naught. And the sixth step is solve this equation for the electric field. So here being the flow chart, let us try to put this into use. From your PU examination perspective, we have Gauss's law applied to 3 cases. What are all the 3 cases? The 3 cases that we are going to discuss are here. Which 3 cases? Number 1, we are going to consider a long line of charge and obtain the expression for the electric field near it. Second, we are going to consider a large sheet of charge and get an expression for the electric field. Third, we are going to consider a conducting sphere, get the field due to that charged conducting sphere. So these are the 3 cases. Now first case. What is the first case? The first case is electric field due to an infinitely long straight charged wire using Gauss theorem. Remember, these 3 are extremely important from your PU examination. One of these 3 is generally asked in your PU examination. So let us take up this discussion. Electric field due to an infinitely long straight charged wire using Gauss's theorem. How do we do that? Now you may notice that this is an infinitely long straight charged wire. That's correct? Yes. Now I will show this construction. This is a long line of charge. Let's assume that lambda is the linear charge density and we are interested in finding the electric field at a distance r. Now let us apply Gauss law. What are all the steps? Recall, the steps are: number 1, identify the symmetry. What type of symmetry is that? You can answer that. Yes, it is cylindrical symmetry. If it is cylindrical symmetry, what type of Gaussian surface should be constructed? That is your second question. What type of Gaussian surface should be constructed? Can you think? If it is linear charged or cylindrical symmetry, we need to construct a coaxial cylinder. So step number 1, it is linear charge distribution. Second step, the Gaussian surface should be coaxial cylinder. It should be a coaxial cylinder. So shall we construct that coaxial cylinder? Yes. Now while constructing the coaxial cylinder, you should be extremely careful. What care should be taken? This is coaxial. That means two things should happen. It should be coaxial, and this coaxial cylinder must have radius r. So this is what we are going to do. This is your Gaussian cylinder. This is your Gaussian cylinder. Apologies for the bad handwriting. So this is the Gaussian cylinder. Now what is the third step? Use flux is equal to net charge by epsilon naught. And the fourth step is to find out flux using EDA cos theta. To do that, let's assume that L is the length of this cylinder. Now I will go to the next slide and show a better picture of this situation. Here it is. You can see that? Yes. Now this diagram shows several things. It shows some E, it shows some n cap, it shows some 1, 2, 3, etc. What are those? Yes. Let's try to understand these things. See, look at this. Here we have got a cylinder which is already constructed. So that job is already done. Somebody has already drawn that nice beautiful cylinder around this charge distribution. Now let us put the third step into use directly. Which is the third step? Flux is equal to net charge by epsilon naught. So flux is going to be net charge divided by epsilon naught. Good, the denominator is very simple, epsilon naught. Now what is the net charge enclosed? Let us try to understand. Now see, this is the portion inside the Gaussian cylinder. Can you see that? This is the portion which is inside the Gaussian cylinder. The rest of it is outside. So what is the length of this Gaussian cylinder? L. So what is the length of the wire inside the Gaussian cylinder? That is also L. So what must be the charge enclosed? Can you guess? Charge enclosed is equal to lambda into L. Is that not correct? You may ask how? Just go to this equation. Lambda is equal to Q divided by L, and this time Q enclosed divided by L. So what do I have? Net charge enclosed is equal to lambda into L. That becomes my equation number 1. Hope you are getting that point. You can just pause the video in case you are getting confused. You can just think for a moment. So we have net charge as lambda into L. That is my equation number 1. Then what is the second equation? That is a critical equation. Flux is equal to E dot dA, or this is E dot A, which actually becomes E A cos theta. So now let us try to understand this equation in detail. This needs a lot of explanation. Let us do that. This flux is flux over 3 different surfaces. Flux over the surface 1, which is curved surface. Flux over the top surface, which is plane surface. Flux over the bottom surface, which is also plane surface. This is equal to E A cos theta. Hope you are getting that idea. flux over the plane surface 3, flux over the plane surface 2, flux over the curved surface 1. Correct? Yes. Now the right hand side contains E, electric field, which we want to calculate, A and cos theta. Now I will go back to the next slide, show the construction and then show how to go for this. This is a beautiful diagram here. However, I am just drawing a rough diagram. This is the construction. Here is your line of charge. Now I want to draw the field line pattern. How do I draw that? The electric field is radially away from a line of charge. This is the front view. Now suppose I consider the top view. What is the top view? The top view is like this. This is the line of charge which goes into the plane of the paper, and this is your Gaussian cylinder. So you may notice that this is the pattern of the electric field lines. Is that correct? Yes, beautiful. Now suppose this is my point under consideration. Electric field is along this direction. The area vector dA is also along this direction. Next, I will choose one more portion here. E is along this direction. dA is also along the same direction. I'll choose one more portion. E is along this direction. dA is also along this direction. So do you notice that everywhere area vector and field vector are parallel to each other? Do you notice that? Correct or not? Yes. So if I go back to my earlier expression, flux is equal to, what did we write? E dA cos theta, which actually became E A cos theta. How do we write that? So remember, the left hand side contains three parts: flux over the surface 1, flux over the surface 2, flux over the surface number 3 is equal to E A cos theta. Now let us look at these things. This is surface 1. This is surface 2. That's right. No, we wrote this as surface number 1 and this as surface number 2, this as surface number 3. Good. So now if you look at the top surface, the electric field is along this direction, while the area vector is along this direction for the top surface, while for the bottom surface the same story. Those two are perpendicular, while for the curved surface electric field and area vector are parallel. So if I choose each one of them one by one, for this surface what do I have? I have theta as 0, while for the second one theta becomes 90, and for the third part theta becomes 90. Is that not? Yes, because for the curved surface 1, area vector and field vector are parallel, while for the other two they are perpendicular. So what do I have? I have flux is equal to E A cos 90, cos 0, I'm sorry. That is my equation number 2. Thus, now we can combine equations 1 and 2. What are equations 1 and 2? Equation 1 and equation 2 can be combined. EA cos 0, that is 1, is equal to lambda L divided by epsilon naught. Is that correct? Yes. From this we can write E into A. What is that A? A is the area of the curved surface. Is that not 2 pi r L? Yes. This is equal to lambda L divided by epsilon naught. So does this L and another L cancel here? Yes. And from this, do we have the expression for electric field as E is equal to lambda by 2 pi epsilon naught r? Yes. So this translates to the equation of the following form. So the electric field is given by E is equal to lambda by 2 pi epsilon naught r. A very important, beautiful derivation. Understand this concept clearly. You may pause the video for a moment and go back to each step. Try to understand what is done here. Good? Yes, good to go. So, just recapping it, we had a line of charge lambda, and then we considered the point here, and we noticed that the electric field turned out to be lambda divided by 2 pi epsilon naught r. Now, one or two important points in the present context. What's the direction of the electric field here? It is radially away. Suppose I consider this point, it is radially away. What if I consider here? It is radially away. What about here? Radially away. What if I consider the top view? This is your line of charge and this is your Gaussian cylinder. So the electric field is radially away from this one. So try to visualize it. It is not so easy to visualize. You can just imagine a comb, basically a comb which curls the hair. So can you try to visualize that? A comb which curls the hair. So can you just visualize the spikes of that one, or say the comb brushes? So in that case, the brushes are all radially away. The bristles are away, right? The bristles are all away, and that's what the electric field representation in the present case is. All right, good. Now, having said that, electric field is given by E is equal to lambda by 2 pi epsilon naught r. It is the time to write it in the vector form also. We can write it in this form. E is equal to lambda by 2 pi epsilon naught r. I will write it as r cap. What is that r cap? R cap is the unit vector along the direction of electric field. So many a times we represent the electric field in the vector form like this, the magnitude being given by E is equal to lambda by 2 pi epsilon naught r. Good. So here is the summary of that result. E is equal to lambda by 2 pi epsilon naught r is the electric field due to an infinitely long straight charged wire. And of course we have used Gauss law. Now let us try to do an important thing here. Suppose we consider representing electric field versus distance graph. This is R and this is E. So we are trying to draw E versus R graph. How do I do that? Simple. Electric field, as you have noticed, is inversely proportional to R. And you all know how to draw an inverse relation graph, correct? For example, last year you may wish to recall what you did last year. You did Boyle's law. Did you learn this one? Pressure is inversely proportional to volume. Or did you learn in mathematics that y proportional to 1 by x gives a specific kind of graph? Do you recall that? How to do that? Try to look for the asymptotic behavior. As r tends to 0, E tends to infinity. As r tends to infinity, E tends to 0. These are the two key steps. So how do I do that? as r tends to 0, E tends to infinity, and as r tends to 0, E tends to infinity. Right? So this is our representation of E versus R graph. An approximate graph, not a very beautifully looking graph, but try to understand how to represent it. These are all possible 1 marker or 2 marker questions pertaining to graph. This question, which is based on Gauss Law, is an important derivation from your PU examination. So, just a recap, electric field due to an infinitely long straight charged wire is given by lambda by 2 pi epsilon naught r. Good. So, how many derivations did we do? We did 1 derivation. What is it about? It's about line of charge. How many derivations we are supposed to do? 3. What are all the other 2 in Q? Second one is about sheet. Third one is about sphere. Good. Let's go to the second one. Electric field due to a plane sheet of charge using Gauss's theorem or Gauss's law. Let us do this one. So here is a sheet of charge. You can visualize the charge itself to be distributed in the form of a large sheet. For example, you have taken a very thin paper and you have pasted charges on that. An analogy, of course. And the surface charge density is sigma. And you are interested in getting the electric field at a distance r from the surface. Hope you are getting that picture. Here is a sheet of charge whose surface charge density is sigma, and we want to get the electric field at a distance r from this large sheet of charge. Remember, it is a large sheet of charge, it is not a small one. What does that mean? It means that it extends up to infinity along these dimensions. It's very large, something like a very large wall. Okay, good. Now we need to identify the kind of symmetry, etc. That means the steps. What are all the steps? Again, you may wish to recall, the first step is to identify the symmetry. What type of symmetry is that? It is planar symmetry. If it is a planar symmetry, the question is what kind of Gaussian surface should be chosen? What kind of Gaussian surface are we going to choose? It is generally a cuboid or a cube or a Gaussian pillbox. Maybe a cuboid or cube or maybe a pillbox. What is that pillbox? You just visualize a capsule, a medicine capsule, right? Or maybe a can, maybe a Coke can. Then what is the third step? Third step is using Gauss's law, which is flux is equal to net charge by epsilon naught. What is the fourth step? Basic equation, flux is equal to E dot dA. What is the next step? Combining them and finally solving it for electric field. Good. Now I will show what kind of Gaussian surface is constructed here in the next slide. Look at this. This is the Gaussian surface. Can you visualize it? A cylinder has pierced through this sheet. This cylinder, something like pillbox, is our Gaussian surface. That's correct. This is our Gaussian cylinder, Gaussian surface. Now, this is a large sheet of charge and I'm showing a diagram here. This is the side view. From this sheet of charge, the electric field lines are like this. They are away. The electric field lines are all away from this sheet of charge. Or if you look at this diagram, for example here, the electric field is perpendicular to it. It is along this direction and they are all uniformly going away. The field lines are all distributed like this. Hope you are able to visualize it. Visualize it very, very clearly. It's very important to visualize this construction. Okay, good. Now it's the time to go to the actual derivation. So how do I do that actual derivation? Let us do this. I'm doing it in the form here. This is my sheet of charge and the charge density is sigma. So this is the Gaussian surface which I selected. Correct? If you look at the previous diagram, this is the Gaussian surface. Now this Gaussian surface has three surfaces. Which three? Flat surface 1, flat surface 2 and curved surface 3. Flat surface 1, flat surface 2 and curved surface 3. I am showing the electric field. The electric field is along this direction. It is along this direction. This is the direction of the electric field. Now electric field is along this direction. Fine. What about the area vector? Area vector for this is along this direction. Area vector for this is also along this direction. But what about the area vector for the third? It is along this direction. Correct or not? Yes. So this is our initial construction. I'll go back to the previous slide to show the same thing. Look at this. He has shown the area vector along this direction, area vector along this direction. Right? This is our area vector. This is our area vector. While for this surface, the area vector is here. This beautiful diagram shows the same thing. Let us go back to our construction. Now, did we do the first step? Yes. What was the first step? Finding the kind of symmetry. We noticed that it is planar symmetry. Good. What about the second one? We constructed the Gaussian surface. This is my Gaussian surface. And the third step is now, what is that? Flux is equal to net charge divided by epsilon naught. Net charge divided by epsilon naught. Now let us do this job. So what is it going to be? Epsilon naught. Net charge. So look at it. This portion of the sheet has pierced through the Gaussian surface. And it must be sigma into A. How is that? By definition, sigma is charge enclosed divided by A. And that gives me Q net is equal to sigma into A. Good. So then we have flux is equal to sigma A divided by epsilon naught. That's my equation number 1. And the next step is flux is equal to E A cos theta. But now let us be a little careful. What are all those things or what is the care to be taken here? Let us see. Now this is the net flux. That is nothing but flux. Net flux is equal to flux over surface 1, flux over surface 2 and flux over surface 3. That's right. So this is what we have right now. So now net flux therefore is equal to this part for the surface 1, that is E A into cos 0 y0. Look at this diagram. This part E and A are parallel to each other. Then for the second part, look at here. So E A cos 0 one more time. third part, E A cos 90. Where is that 90 coming from? For this part, the flux is along the curved surface while the area vector is perpendicular to it. So what do I have? I have EA cos 0 is 1, EA cos 0 is 1, EA cos 90 is 0. So I have 2EA. That's my equation number 2. Good. So now I have net flux is equal to 2E into A. Now, what was my equation number 1? Flux is equal to sigma A divided by epsilon naught. What is my second equation? Flux is equal to 2EA. That is net flux. This is also net flux. So if I consider them as equations 1 and 2, I can say 2EA is equal to sigma A divided by epsilon naught. So what do I have? From this equation, A and A cancel and I have E is equal to sigma divided by epsilon naught. Good. 2 epsilon naught. I'm sorry, I missed out that 2. So E is equal to sigma divided by 2 epsilon naught, and again a very important equation. E is equal to sigma divided by 2 epsilon naught. Good. So this is a sheet of charge and the electric field at a distance r is given by sigma divided by 2 epsilon naught. Did you notice a very important thing? Number 1, the electric field is away from it. Second, most importantly, this equation tells me that it is independent of the distance r. There is no r term in this equation. What does that mean? It means that the electric field has the same value at all the points near a large sheet of charge. I repeat this statement one more time. The electric field has the same value at all the points near a large sheet of charge. And what is the strength of that field? It is sigma by 2 epsilon naught. And is the direction same at all the points? Yes. So what type of field does it produce? It produces a uniform electric field. It produces a uniform electric field, and this is what was discussed when we did electric field, uniform electric field, non-uniform electric field, etc. So do you recall that there was a diagram of this kind showing the uniform electric field? Do you recall that? Yes. This is the electric field due to a large sheet of charge. So here is the result. If you consider a large sheet of charge having a uniform surface charge density sigma, then the electric field is given by sigma by 2 epsilon naught. And we can show it vectorially. This is your r vector and the electric field is given by E is equal to sigma by 2 epsilon naught r cap. This is a r cap which is along the direction of the radius vector, or say along the direction of the electric field. Now you may wish to draw a graph of electric field as a function of r. So how to do that? Probably many of you have figured it out very easily. Correct? The electric field is independent of the distance, so clearly this is a graph indicating E versus R behavior. Good. So what did we do? We did two things. One, we got the electric field due to a line of charge. Two, we got the electric field due to a large sheet of charge. Correct? Now we are left with the electric field due to a conducting sphere, a spherical conductor. This is one of the very important things both from understanding perspective and problem solving idea also. One of the very important derivations as well. Let us try to do this one. Electric field due to a charged spherical conductor. Okay, what have I got here? I have got a spherical conductor. And remember, it is a spherical conductor. And when you studied the properties of conductor, did you come across with the concept that charges stay only on the surface of a conductor? Yes. Which means that whether this conductor is solid or hollow makes no difference. It makes no difference. So whether we are considering solid conductor or hollow conductor, the end result is going to be the same. So let us try to do this. Now we have got a spherical conductor and the charges are sprayed on that spherical conductor, and these charges get distributed uniformly on the surface of the conductor. Assume that the radius of this sphere is r, and we are interested in finding the electric field at a distance r outside the conductor, and then at a point here on the surface, and third at a point inside also. So these are our three targets: electric field at a point outside, electric field on the surface, and electric field inside as well. So outside, on the surface, and inside. Let's try to get that one. Now again, our job is very similar as we did in the last couple of discussions. The first is to assume a total charge Q. I'll assume that charge density is rho, charge is Q. What type of symmetry do you notice? Yes, correct. You notice a spherical symmetry. Good. What type of Gaussian surface? You notice that this has to be a concentric sphere. Good. So I have drawn a concentric sphere. Apologies for the very poor diagram here. So you got a spherical Gaussian surface. This is the Gaussian surface. So we did the first step, we did the second step also. Now what is our third step? Third step is to find out flux using Gauss law. Net charge divided by epsilon naught. Isn't it? Net charge divided by epsilon naught. Now let us try to do this one. Denominator is simple, epsilon naught. Now total charge present on the conductor is Q. So how much charge is captured inside the Gaussian surface? The total charge captured is Q. So flux is equal to Q divided by epsilon naught. Hope you are getting it. You may wish to pause the video, get the things clear, and then proceed in case you are not following. Okay, good. So here is the diagram for our purpose. That means now I have to go to the third step, or say fourth step rather. That is, flux is equal to E dA cos theta. So look at the beauty of this problem. The electric field due to a sphere is radially away from it. You take any point for that matter, the electric field is radially away. Here the electric field is radially away. The electric field is radially away here. So it is radially away everywhere. So we know this. Electric field is along this direction. dA is also present. What is the dA? dA is the area of the small portion on the Gaussian surface. Theta. Cos theta. What is that theta? Theta is the angle between the electric field and the area vector. Look at this. This is the direction of the electric field. Do you notice that? This is the direction of the electric field. Do you also notice that the area vector is along this direction? That is right, because it is perpendicular to the surface. So, are not electric field and area vector parallel? Yes. So, what must be? This must be 0. So, what do I have? I have E into dA. And thus, this being d phi, the net flux is equal to integral E dA. That becomes E into integral dA, correct? E integral dA. What is the meaning of integral dA? It simply means total area of the Gaussian surface. What is the total area? It is 4 pi into r square. Notice that this is small r. So what do I have? I have flux is equal to E into 4 pi r square. That's my equation number 2. Correct? Yes. So it's the time to combine those two equations. Let's do it here. So flux is equal to Q by epsilon naught was our equation 1, and flux is equal to, what was that? E into 4 pi r square is my equation number 2. So if we combine them together, we have E into 4 pi r square is equal to Q by epsilon naught. So let us simplify it further. We have E is equal to 1 by 4 pi epsilon naught Q divided by r square. Correct? E is equal to 1 by 4 pi epsilon naught Q by r square. Very good. Now, you might be thinking that I have come across with this equation somewhere else. Yes, that's a good observation. What is that? Look at it. This is the beauty of this problem. You had a spherical conductor carrying a charge Q whose radius is r, and this is where the point is located, and the electric field here is 1 by 4 pi epsilon naught Q divided by r square. Now instead of this spherical conductor, had you considered a charge Q at its center, the electric field at the same point would have been given by the same expression, 1 by 4 pi epsilon naught Q by r square. What does that mean? That's a very important observation. It means that this spherical conductor is as good as a point charge. It is as good as a point charge placed at the center of the sphere. So keep this remarkable result in mind. A spherical conductor is as good as a point charge placed at the center of the sphere. We get the same type of results, correct? Thus, the electric field due to a charged spherical conductor at a point outside is given by this expression. Now, the second is the electric field on the surface. So we have this one. This time it becomes simpler. R, Q, and isn't your R equal to R? That's correct. So your expression for the electric field becomes 1 over 4 pi epsilon naught Q divided by R square. Fairly simple, pretty simple. So on the surface, that means if I consider the electric field at this point, it becomes 1 over 4 pi epsilon naught Q by R square. Good. Then at a point inside, This is your spherical conductor, and this time the point is at a distance r, and this is your capital R, and charge q is present inside. Probably some of you are thinking that the electric field inside is given by 1 by 4 pi epsilon naught q divided by r square. No, this is not correct. Why is it not correct? This is not correct for the following reason. How did we arrive at this equation? Just recall. We did flux is equal to q enclosed, or say q net, divided by epsilon naught, and we combined it with the equation flux is equal to Ea cos theta. But this time if you look at it carefully, we have net charge as 0. Is there any charge inside? That means if I consider a Gaussian surface here, do I have any charge enclosed by the Gaussian surface? No. So this part is 0. If this part is 0 and if we equate them, then clearly we get electric field is equal to 0. Hope you are getting that point. Thus, on the surface, the electric field is given by 1 by 4 pi epsilon naught q divided by r square, and at a point inside, the electric field is 1 by 4 pi epsilon naught q by r square. No, it is not. It is 0. Remember one more time. So here is the summary of that one. At a distance r, remember the distances are always measured from the center. That's an important thing to be kept in mind. The electric field is given by 1 over 4 pi epsilon naught q divided by r square, where r is the radial distance and q is the charge present on the spherical conductor. And this result is valid both for solid as well as hollow spherical conductors. Hope that point is clear to you. It is applicable both for solid and hollow spherical conductors. So here is the summary. The electric field at a point outside the charged spherical shell is 1 by 4 pi epsilon naught q by r square n cap along the electric field. On the surface of this sphere, it is q by r square, where capital R is the radius, and inside the electric field is 0. And here is the graphical representation. So observe that I am at the center, the electric field inside is 0, and I go from center to the surface, the electric field still remains 0. So at the center the field is 0, I am going up to the surface, the electric field remains 0. And on the surface, the electric field is 1 by 4 pi epsilon naught q over capital R square. And electric field at a point outside is 1 by 4 pi epsilon naught q divided by small r square. That means now outside it is 1 by r square dependence. That is what we have seen here. So this is the kind of variation. And the electric field is maximum at the surface, isn't it? The electric field is maximum at the surface. And outside it is 1 by r square dependence. Good. So let us just look at the summary of these three things. Number 1, for a line of charge, remember it is long. It is a long line of charge, infinitely long. So we can show it like this. It extends up to infinity. The electric field is given by lambda by 2 pi epsilon naught r. And for a sheet of charge, and again large sheet, obviously this is a large sheet of charge, the electric field at a distance r is given by sigma by 2 epsilon naught, and the electric field due to a conducting sphere. Remember, it could be a solid, it could be a hollow one, anything for that matter. The electric field at a distance r outside is given by 1 by 4 pi epsilon naught q divided by r square. What is that q? It is the charge on the outer surface, and r is its radius. The electric field at a point on the surface is 1 by 4 pi epsilon naught q divided by r square, while the electric field at a point inside is 0. These are very important set of results. They are very important set of results. Now remember, these three cases can be converted into various results. For example, I'll take up a very simple case. Let's try to understand. Imagine you have a sheet of charge, large sheet of charge. Now what is the electric field at this point? If it is carrying positive charge, the electric field here is away from it and has a value sigma by 2 epsilon naught. What if I consider the point here? Again the same story. The electric field is sigma by 2 epsilon naught. Now let us consider one more situation. This time I have two sheets of charge, for example plus sigma. Remember, this is a sheet of charge, and I have one more sheet of charge plus sigma. Charges are all present everywhere on this sheet, just like this. I can show the charge on the sheet. Now the question is, what about the electric field? This is sheet number 1, this is sheet number 2, and this is our point. Now the sheet number 1 produces the electric field along this direction. Sheet number 2 produces the electric field in the opposite direction. So it produces the electric field in the opposite direction. So it is in this direction. Correct? Yes. This is the point. So here sheet number 1 produces the electric field in this direction. Sheet number 2 produces the electric field in this direction. Here sheet number 1 produces the electric field in this direction. Sheet number 2 produces the electric field in this direction. And how to find out the magnitude of the electric field at these points? That is our discussion for next class. I'm just leaving you with a thought process. Remember this important concept. Alright, so just a quick recap of what we did in today's class. The electric field due to a line of charge is given by lambda by 2 pi epsilon naught r. Due to a sheet of charge, sigma by 2 epsilon naught. Due to a conducting sphere, it is 1 by 4 pi epsilon naught q by r square. And due to conducting sphere on the surface, 1 by 4 pi epsilon naught q by capital R square, and at a point inside it is 0. Alright, so please complete the lecture number 1.8 homework corresponding to today's class. Alright, so internalize these concepts. These are very important. See you all in the next class.